Thank you very much for the opportunity to be presenter here. I'm happy to share our results with you. This is the outline of my presentation. Actually, the presentation aims to provide a background about the technology of lead-free ferroelectric materials for sensing applications. So it is about the practical applications of the devices using these materials. Therefore, the presentation doesn't consider the theoretical analysis or fundamental science, but it is like a different engineering point of view about how the fundamental science could be used in the practice. So I will start with a brief introduction to the ferroelectricity. The schematic here on the upper left side of the slide could give an idea what is the relation between the dielectric, piezoelectric, pyroelectric, and the ferroelectric materials. So actually, dielectric materials are electrical insulator that could be polarized after external field is applied. So the piezoelectric materials are a group of dielectrics that could show a change in their polarizing ability, strain or stress due to applied electrical field, and vice versa, the process is reversed. So the pyroelectric materials are classes of piezoelectric materials that could change their polarization also after the change of the temperature. And the ferroelectrics could combine all these properties. So due to this multiple functionality, it could be integrated into the physical sensing element that could detect simultaneously mechanical loading and change in the temperature. Later, I will give a slide for concrete practical applications where and why we need such kind of device. But in general, the ferroelectric materials possess so-called spontaneous polarization, so they do not need an external electrical field to prepolarize the material. So the all properties that could be mechanical, electrical, and thermal are all connected in this kind of materials, and they could be quantitatively expressed by the corresponding coefficients. So here, this is the piezoelectric modulus, the pyroelectric coefficient, and electrocaloric coefficient, which is not considered in this presentation because it is out of the scope of our study. But actually, these coefficients could be tailored by proper materials engineering, and particularly by the chemical composition and crystal lattice structure of the materials. And these characteristics are strongly dependent on the deposition technology for thin film fabrications. Here I provide some images about to explain what happens inside in the materials in this case. So this piezo, pyro, or ferroelectric effects are possible only for non-central symmetric structures or lattice. that should be polar in addition. It means that the crystals have no mirror plane and has no two-fold axis perpendicular to them. The most commonly used material in this case is the lead zirconium titanate. It exhibits the strongest piezoelectric module and pyroelectric coefficients, but unfortunately it is toxic in the recent few years. So another concept is introducing in the material science for lead-free environmental friendly materials. So we should replace somehow this lead zirconium titanate with a material which is without lead containing in its chemical composition. So there are some possible alternatives like barium strontium titanate and zinc oxide. However, they exhibited poorer or not so stronger dipole moment ability formation, so their piezoelectric and pyroelectric coefficients are lower. Then the challenges, some general questions appear in this case. Can we use materials that are lead-free, consider environmental friendly, at the same time to have enhanced lattice asymmetry or ability to produce a dipole moment? So this would result in generated stronger piezoelectric and pyroelectric response. And at the same time, the third condition, could we produce them by conventional microfabrication technology? So they could be in this way compatible with all other sensors or silicon readout circuits manufacturing. And if yes, if the answer is yes, then how we can control their properties, how we can produce nanostructure of these films, because later you will see this affects strongly on the sensitivity and the performance of the sensors, and which films parameters exactly would be the most crucial for the device performance. So our team tried to answer all these questions. And it is important to answer this question because of the applicability of such kind of ferroelectric sensor. So especially in the medicine, in biomedical engineering, in the automotive industry, climate change monitoring, motion detections, and so on and so on. A lot of application could be pointed out here, but maybe the most important are the wearable physical sensors that could be attached to the human body and could collect some data from the body organism about the activity of the person and could give conclusions about the health conditions. So in this case, you will need a pressure sensor, you will need a temperature sensor to map the body temperature, you will need a strain sensor to follow the muscle movement, etc. But you don't need to combine wearing all these separating physical sensing elements on your body. It would be better if it is possible to combine all this in one single sensor integrated platform. That's why the ferroelectric coatings are really important, because they can combine both. And I will move to our contribution to the field. First, I will talk about the lead-free ferroelectric coating from zinc oxide doped by gallium. This is actually doping approach that is applied to increase the electrical conductivity of the piezoelectric film and to give better sensing ability and greater measurable signal, because it is important for the noise escapability. Different coatings were produced by conventional vacuum sputtering in radio frequency electrical field process on silicon substrates. And the experiments were conducted at different sputtering voltages and different sputtering pressures. Briefly, about those of you who are not familiar with this process, it is a vacuum chamber. Inside you mount the substrate and the target material that you want to be grown as a thin film. You fill the chamber with specific concentration of inert gas and supply the sputtering voltage. It is causing ionization of the argon ions. Then the positive argon ions are extracted from the fields, accelerated to the target material, from example, zinc gallium oxide, and eject or sputter some nanoparticles or molecules from the materials that are arranged on the surface. But according to the pressure and the voltage, the dynamics and kinetics of the process is different and the deposition rate is different. It could result in a different crystallite formations and different surface morphologies. As you can see here, this is the atomic force microscopic images of the coatings produced from these materials at the different combinations of growing conditions. They are characterized with different degree of roughness, and we should select the smoothest one with relatively low roughness as compared to the other ones, because it will need to contact further electrically with the electrodes, with the electrical contacts serving as extractors for the signal. And in this case, we can see two smooth surfaces characterized with 2.5 nanometers average roughness and 6 nanometers average roughness. Then the second criteria is to form a crystallite structure, not amorphous, because otherwise there will be no polarization effect in these coatings. So from the two combinations, we select this one that is produced at the higher sputtering voltage, because as you can see from the X-ray diffraction, it means that these peaks and their sharpness means that specific crystallite formation following single axis orientation are growing, and this is favorable for the polarization process. So this case we select for further fabrication of our device. Our device is fabricated by a conventional microelectromechanical system, bulk micromachining process. It means deep anisotropic chemical etching of the silicon wafer, and in a specific region, this inner square here in this image, which is 1 millimeter and 1 millimeter in square, it becomes thinner and its Young modulus is changed. So it is transferred from solid, rigid substrate to flexible, only locally here. Then this flexible micromembrane is coated with piezoelectric coating. This is the way of transferring of mechanical loading on the piezoelectric film, and on the top some aluminum contacts are deposited. And here what we can see that the maximum piezoelectric coefficient that is measured for low frequency of 16 Hertz at low mass loading of actually these are 800 grams per square millimeters, could reach almost 100 picocoulomb per Newton. This is good value considering the lead-free materials and considering the total thickness of the coating, which do not exceed 400 nanometers. And the voltage that is generated from the piezoelectric coating could range from 10 to 100 millivolts when the operational range of mass loading is between 2 and 800 millimeter square, a gram per square millimeter. Apologizes for the error. So it is considered as a high sensitivity and broad operational range sensor. So further study of the sensing behavior was conducted with this potassium niobate, again lead-free ferroelectric material, again grown by radio frequency vacuum sputtering. And here the same approach we use to find the best surface morphology, guaranteeing smooth coating in good contact with the electrodes. Again, we tailor the plasma power, the plasma voltage actually, and the deposition rate, as well the concentration of the argon sputtering pressure. So for the optimal case, this is produced at 0.9 kilovolts, the total thickness of 900 nanometers of potassium niobate. You can see almost 400 millivolts and 5 microamperes could be produced from 4 square centimeter area of the sensing element and application of up to 3 kilogram mass loading. This is the maximum possible loading that could stand from the element without to destroy physically. And you don't need even to fabricate a micromembrane. So due to the excellent smoothness, the roughness is less than 8% from the total thickness. We achieved a very stable coating after 1000 cycles of repeating press release stress application. So the deviation from as compared from the fresh sample is only 2.2%. And as you can see, the signal itself, it is characterized with great periodicity, without nonlinear distortions, which is very favorable for the single conditioning system for the electronics that could further process the signal from this element, because you don't need special filtering and so on. I have a special slide devoted to this system at the end. The piezoelectric coefficient measured at 40 grams only per square millimeter is better than 250, which is really competitive with the lead PZT, lead zirconium titanate. So it is a contribution to the field. And by Fourier transform infrared spectroscopy, we are able to detect the reason for this strong piezoelectric response. It is due to presence of several non-centrosymmetric lattice formations, unilattice cells. They're more asymmetric than the pure cubic, and they are tetragonal, ortho, rhombal, and tetragonal lattice. So I will not go into the details. Everywhere at the bottom of the slides you can see the reference to our publications where some specific details could be found. I will move to the nanostructuring of these lead-free materials and how this nanostructuring affects the sensor performance. If we can convert this dense coating into nanowires, nanodendrites, or some other nanostructures, we increase their surface to volume ratio, and thus we can increase their functional area by keeping the overall size of the element small and compact. One of the approach that we used, we applied for the potassium niobate. It was anodization of aluminium oxides. So aluminium is subjected to a chemical process of anodization, and during this dissolving of aluminium, it is oxidized, but forming specific kind of an array of nanopores. And if the thickness of the aluminium is high, these nanopores become nanotubes. And they could give a good template to fill these nanotubes with our functional ferroelectric coatings, then to dissolve the nanotubes and to remain attached to the surface only nanowires. But they are very regularly single axis organized because they strictly follow the template of this aluminium oxide. And the filling of the nanotubes is again by conventional microfabrication sputtering process. At the bottom of the slide, you here see scanning electronic microscopic images of the top of the pores. It's captured at different stage of filling. Here it is completely empty and filled. Here it is partially filled with potassium niobate, and the right side completely filled with the potassium niobate. So here you can see the cross section of these nanowires. These images present different lengths of the nanotubes. Here is the shortest 1.3 average length, and here it is about 10 micrometers. So what could be noted here? The piezoelectric voltage could be doubled as compared to non-structured material with a similar volume. Now, here we cannot compare the thicknesses, we should compare the volumes. And we can see that it could almost linearly increase with the nanotube length with 16 microvolts per micrometer, and there is a superlinear dependence between the mass loading and the piezoelectric voltage, which is actually our aim for any kind of sensor device, because it gives a direct relation between the quantities. If we compare the signals, again, there are some distortions. Of course, it is expected because on the top, the contacting electrode could realize only the point-to-point contact, not so regular and uniform like for the dense coating, but the distortions are less than 10%, so it could be easily filtrated with the proper electronics. So we found that the pyroelectric response is not so sensitive to this nano patterning, but it could provide a measurable pyroelectric voltage with a sensitivity of 400 nanovolts per micrometer, and it is active in the time range really close to the most of the human interested applications, 30-40 centigrade, making it suitable for healthcare applications, body temperature change monitoring. So to the best of our knowledge, this is the first time of multi-sensing device involving combination of these materials. Another approach that we used, it is to realize heterointerfaces, growing ferroelectric oxide, not over conventional metal electrode, but over electroconductive polymer, or this serves like amorphous seed organic layer. As a result, the growing gallium-doped zinc oxide here for this experiment possesses nanodendrite, nanoporous structure. If we decrease the content of gallium and getting close to the pristine zinc oxide, these dendrite formations are converted into nanoleaves formations with the typical sizes ranging between 300 and 500 nanometers. It doesn't matter the concrete dimensions. Actually, in both cases, what is important that surface to volume ratio is increased, so it could result in, you will see on the next slide, triple increase of the voltage produced. And here are given some X-ray diffraction patterns that prove that the typical features, if we compare with the standards, if we compare with materials without seed layer, could be formed. And these are typical feature, but the strongest is this one at 33 degrees 002 plane, which is corresponding to a C-axis preferential orientation of the crystallites of the nanodendrites, which is favorable for the fluent polarization. So as you can see the signal before and after the seed layer introduction, and comparison in linear plot according to the mass loading. The linearity is not strongly affected, but at the same time, even at small mass loading of few grams per square millimeter, it is almost double, and at the largest mass loading almost triple. Increase of the sensing reaction, and here it is presented the polarizing ability, the hysteresis loop after nanostructuring. It is narrow. It means the small driving force that causes polarization as compared to the non-structured material, which could be considered as better sensing ability. And here is the ferroelectric voltage in both cases, nanostructured and non-structured, non-patterned coatings. As you can see, the hysteresis loop, which is the average difference between the cycle of cooling and heating. At the non-structured materials, it is average 35 millivolts, which is equal to almost 30%. This is the error in the sensor, and here the average is only 20 millivolts, which is less than 5% of errors. I'm almost at the end of my talk. We characterized the sensor devices using impedance spectroscopy. It is important to extract the full impedance because it is important to find the impedance matching conditions with signal processing electronics, and in this way we extract some information about the internal resistance, about the interface capacitance, which directly affect the time response of the sensor, sampling rate, taking the signals, some parasitic effects like parasitic capacitors and parasitic inductors from the leads, from the packages, and so on. So these intrinsic materials properties could be easy scanned, easy probed by impedance spectroscopy. So we did this for the potassium niobate, we determined this its equivalent electrical circuit. We calculated from this model that better fits the experimental results, the concrete values for the capacitance of the interface, internal resistance, full impedance, and parasitic components, etc. And we did the same for the potassium niobate. The previous one was for gallium doped zinc oxide, I'm sorry. We found that the potassium niobate is strongly sensitive to the thickness, and if it is greater thickness than 600 nanometers, some overtones could appear in the characteristics, so they can introduce noise in the sensing channel, so should be avoided such kind of thicknesses. This is for design point of view. And finally, we designed the proper single processing for the producing sensor. It is like an interface circuit. It is based on field programmable analog array. It could realize root mean square to DC conversion process by configurable analog blocks that could be programmed in the special kind of software, Anodyne Designer. And you can actually make such system universal and reconfigurable by programming, and you can easily replace the materials involved without to change physically the components realizing the signal conditioning systems. So here it is the demonstration of the working ability of this electrical circuit. It is switched as a differential amplifier. To obtain the output DC voltage, it should be DC, although in the piezoelectric mode, it is alternative current at the input. And there should be correspondence between the two values, no matter of the mass loading. So we achieved at small mass loading less than 1% divergence, which is excellent accuracy of transformation of the AC to DC signal. So the conclusions I will not read in details. I believe that you catch the idea. I will only highlight the future work. It will be development of fully implantable, fully organic sensing element. We are trying currently to replace the ferroelectric oxide with ferroelectric polymers, and to replace the metal contacts with the electroconductive polymer. So this will make our design fully implantable. And thank you for listening to me. This is the members of the group. Thanks to acknowledge their work. Thanks to them for their work, and thank you for your attention.